Okay, so the first thing I would like to say, I've heard that the images are not so great here. Oh boy, the keyboard has all the letters in a different place. Okay, I will do my best. Oh man, okay, sorry, this might take a while. Okay, somebody else will post in the chat. There's a link to the lecture notes, and literally everything I'm going to write on the board in this room is in the lecture notes. So if you're attending remotely, what I might recommend is just pull up that PDF and listen, and apologies. But that way you won't have to see my bad handwriting, so it might even be an improved experience. I should really apologize to those of you who are here in the room. Okay, there was something else I was going to say by an apology. I know I'm covering a lot of ground and going fairly quickly. So the first lecture was all meant to convey that there are some significant coherence problems from interpreting the strict syntax of type theory into kind of a more flexible, up to isomorphism universe of one category theory. So the good news I suppose, about the amount of ground that we're trying to cover is essentially none of that material is going to reappear today. So I wanted you to be aware that this coherence problem exists, but we're not actually going to really mention it again. So the one thing that would be useful to recall from yesterday is the following definition, though. So Voevodsky defined a universe in a category as follows. So a universe in a category E is given by, so it was the data of an object, but also a map over it. And then together with a choice of pullbacks along any morphism into the codomain, with sort of for any morphism into the codomain of the universe, a chosen pullback. And the notation that he used was as follows. So this sort of semicolon, any notation that would be fine. And that data defined what was called a universe. So the use of this was from E and U. He had a technique for constructing a contextual category called E sub U. So there was some device out of this to construct a contextual category. That, remember, is our categorical structure that models type theory. And in this contextual category, one of the key structures was something called a display map. This is the thing whose domain can be understood as a context extension of the codomain. And the display maps are given by the data of these specified pullbacks in the universe. Okay. So furthermore, for a contextual category to model sort of an interesting type theory like homotopy type theory that also has all of these logical rules, so the type forming operations for sigmas and pi's and identity structure and so on, the contextual category needed to have corresponding strictly stable structured versions of all of that. And part of Voevodsky's universe technique is to define those structures kind of representably on the universe and then induce it on the contextual category. So we sort of ran out of time to really illustrate that, but for instance, in the lecture notes, you'll see what it means to have for a universe to bear an identity structure, and then the theorem is that the contextual category inherits that sort of structure. So we can see that this universe is really the key device in this approach that is solving all of the coherence problems. So today, what I'd like to explain is how you would actually construct the universe in a particular model that will then satisfy those properties, plus some additional ones. So the intention is not just to construct a model of Martin-Löf dependent type theory, but homotopy type theory, which requires that in addition we have something called a univalent universe. So I'm also going to explain what all of that means. Okay, so today, the key question is sort of how do we define, or how do we find a universe? Or I'm going to introduce new terminology a universe is really a pretty weak thing. Essentially, you just choose a map and choose a whole bunch of pullbacks. But I'm going to define terminology today for something called a universal fibration, which will satisfy a stronger property than merely being a universe. And this is the thing that'll play the sort of central role in constructing the simplicial model. Okay, so the reason I wanted to recall this definition is, again, in the contextual category, the categorical model of type theory that you get out of a universe, the display maps are all defined as pullbacks of the universe. Now, in the simplicial model, so we're going to work largely in the category E, which is a pre-sheaf category on delta, aka the category of simplicial sets. So in the preview to the simplicial model of univalent foundations, we mentioned that there are certain maps of simplicial sets that behave like display maps, that behave like a projection from a dependent type family onto the base context, and those are confibrations. So in this context, what we want is a universal confibration, a universal confibration. And there's perhaps a naive approach to defining this universal confibration that we could write down right away. Maybe I'll call this the Anita idea. So again, the intention of this universal confibration, so now I'm working inside the category of simplicial sets. Well, it's something that if I pull back along any map, I get a confibration. And in the category of simplicial sets, I can consider in particular the represented simplicial sets. These are the n simplices, and consider pullbacks like this. And the idea is that for any n simplex, I have a specified pullback that needs to be a confibration. So the Anita idea then is to define un, the set of n simplices. So by Anita lemma, this is isomorphic to the set of maps here. So I'm just going to define this to be confibrations over delta n. So confibrations over the n simplex. So this is the Anita idea for just defining, we're trying to find an explicit simplicial set that is this universal fibration. I haven't explained what universal fibration means. That's going to be the big definition we're building towards. Okay, but there's some problems with this idea. So the first problem is there's an issue of size here. So if I don't have any restrictions on the size of the simplicial set E, there's sort of too many of them. Even if I do impose restrictions on the size of the simplicial set E, one of the things Egbert mentioned is that in set theory there's a proper class of singleton sets, so there's kind of just way too many sets. So what we will want instead to restrict somehow to a set of small fibrations. And the idea of this smallness is, so we need to impose some sort of cardinality restriction to kind of cut down so this is a set. But there's a second issue which I find even more interesting than the size issues, which are fairly familiar with in set theory, which is an issue of coherence. So what I've defined for you, sort of size issues aside, is a set. Once we've solved the size issues, this UN will be a set of maps. But what I'm trying to define is a simplicial set, which means I need the simplicial operators to define a functorial right action on such sets. And so in other words, so the action by a morphism, so morphisms in the category delta can be thought of as, by the Anita lemma, morphisms between the representables. So the action by this on this set UN, on sort of UN as above, is by pullback. So simplicial sets are contravariant functors, which means that if I had an element in this set, I need to, I would pull it back and obtain an element in the set of confibrations over delta M, but this is pseudo-functorial as opposed to strictly functorial. So a way this is often described is that this construction is defining a simplicial groupoid rather than a simplicial set. So we have two different issues that we're going to solve. So in the interest of time, I'm going to largely sweep this one under the rug. So we're going to sort of hide this issue. So it's very interesting, the solutions to the size issues. The original sources, so Vorvatsky's paper and subsequent work of Mike Schulman really delve into this and deal with it precisely. I'm going to use some language on occasion that indicates how these size problems are being solved, but we could spend the rest of the lecture talking about very subtle issues of large cardinals Or we could talk about the coherence issues, and I'm going to elect to do the former sort of with apologies. But one thing maybe I will give before I hide the size issues is a more precise meaning to this phrase small fibration, which I will use on occasion to indicate that size is something that somebody should think about. So here, a sort of small map. I mean, you can apply this adjective small to an arbitrary morphism, not necessarily a fibration. So a small map means, so firstly, what you might call a kappa small map, where kappa is a regular cardinal. Right now, it'll eventually be inaccessible. And what that means is that meaning any pullback over a kappa presentable object is kappa presentable. So in a category of sets where we are today, I can just say kappa small, meaning the cardinality of the sets are bounded by kappa, but there's a more categorical way to discuss size that will be necessary for the generalization next time when I'm also going to ignore size issues. But capital presentable object, so pullback over a capital presentable object is kappa presentable. So in particular, this notion of size does not require, so I mean, when the codomain is small, it essentially just means that the fibers are small, but the codomain is not necessarily small. Okay, great. So, but let's dig into this coherence issue, because this is, I think, really quite interesting. And it leads us to the following question, which are, what do the fibrations form? And in the answer to this question, I'm going to give a precise definition of what in fact it means to be a universal fibration. This is not something that I understood very well until I was preparing this lecture series. So what do the fibrations form? Well, so maybe a preliminary question is sort of what do the maps in a category, what do the maps form sort of under pullback? So we saw that the issue with this, the coherence issue with this Unita construction is that this pullback action is pseudo-functorial, and I can make that a little bit more precise as follows. So we can work in an arbitrary category E with pullback, so I invite you to read E to be simplicial sets for all of today. And there is a functor, which I'm going to write as blackboard bold E. This is notation that Mike Schulman uses. It's contravariant, and it lands in the large category of groupoids. And how it acts is it sends an object of B to the slice category, except I'd prefer to just take that to be a groupoid. So I'm going to take something which is the groupoid core. So these are the groupoid of isos over B. Groupoid of maps over B. So these are all morphisms with codomain B and isomorphisms between the fibers that commute with the base. So the functorial action here, so if I have a map F from A to B, I can pull back a map over A, map over B to a map over A, and this is a pseudo functor, meaning it's not strictly functorial, but it is functorial up to canonical, sort of a coherent, in this case, canonical natural isomorphism. So that's just what maps give you under pullback. This is the packaging of that. So we're really interested in the fibrations, but we can understand the structure of the fibrations in a category as a sub-functor of this. So sort of a key fact about fibrations. So fibrations are closed under pullback. So this is absolutely true in any model category and for any notion of fibration deserving the name fibrations. So closed under pullback. This follows from the fact that they're characterized by some sort of right lifting property. So it follows that I have a subfunctor. So it's still a functor on E, because that's giving me the objects in the base. I'm going to call this one F. And maybe a way to understand it is it's sending B to the subgroupoid. So here I've written a kind of script F. Sorry, this is meant to indicate that it's a groupoid of isomorphisms. And here I just mean the groupoid of fibrations over B, of vibrations over B. Okay, so this is sort of a more precise statement of the observation that we made that vibrations under pullback are pseudo-functorial. They can be packaged into this pseudo-functor here. Maybe I will mention that if I want to be more precise about sizes, I can be. So if I pick a regular cardinal, I could define an analogous construction where I've given it a subscript kappa for my cardinal, and I could maybe put a kappa here and then add the condition that these be kappa small. So at some point I might have a kappa secretly appear, but I'm largely going to hide these issues of size. Okay, so, right. So let's think about these pseudofunctors. So if I had any vibration or small vibration, if I'm being more precise about size, but maybe let's not. So if I had any vibration in my category E, then by the Yoneda lemma, I suppose here really the bicategorical Yoneda lemma, I could think similarly about the representable functor. This one is strictly functorial, but I could regard it as a pseudo-functor. It doesn't really hurt. I'll mention this again in a moment. It's also valued in sets, but sets are groupoids, so no problem. It lives in this category. And what Yoneda says is that there is a unique pseudo-natural transformation from here to this functor. By the Yoneda lemma, such a thing would correspond to an element in this groupoid over B, namely we take P. So by Yoneda, I have a natural transformation like this. And now this is building towards the question sort of what is then the universal vibration? Or here, maybe I'll actually be a little more precise, the universal small vibration. So what you might think would be an answer is sort of one idea is firstly it should be a vibration, maybe a small vibration. Again, this does not require the base to be small, but it does require that the fibers are small in kind of a general categorical sense, so that when I look at the corresponding pseudo-natural transformation induced by this, here, since I'm saying small, I'm going to give it a subscript kappa, and small means kappa small, whatever that means. So that this induced thing is a natural isomorphism, meaning in particular, for all B, I would have an isomorphism like this. I mean, usually when we say, in category theory, when we say something is the universal blah, we mean that in the language of represented functors. So I would say that pi represents the functor vibrations. Seems totally reasonable. But again, there are some problems. So the problems with this, I mean, are kind of twofold. Number one, E is a one category, so this is a set, and that's a groupoid, and so this isomorphism just seems very unlikely, unless, I don't know, your category is a lot more rigid than I'm expecting. So E is a one category. So this thing on the left is a set, while this thing on the right is a groupoid. So most groupoids are richer than sets, and so that seems unlikely. Another issue is if we think sort of more naively about what it would mean to have a one-to-one correspondence between maps from B into U and vibrations over B, we can see some problems. So if I had a vibration P that is classified, if I had this one-to-one correspondence, then there would be a bijection between vibrations over B and these classifying maps. But we can see that the same vibration could conceivably be classified by multiple maps if there are any, sort of isomorphisms between the fiber and the base, non-identity isomorphisms. And when I compose these pullback squares, I get a different classifying map for the same vibration. And sort of conversely, if I have a vibration, again, that's classified by some map into my universe, and now let's suppose I have a fibered isomorphism. So there's some other vibration P prime that's isomorphic over the identity to this. Then what I see is the same map can classify multiple vibrations. So it's just unreasonable to expect that there's a bijective correspondence between maps into the base of the universe and vibrations over the thing I'm mapping into. So this is not what I'm going to mean by a universal vibration. So this begs the question of what I am going to mean by a universal fibration, and I'll give the definition now. So maybe one requirement I'll make before we lose this board is, so one requirement is that we're going to ask, so we'll ask that our universal fibration weakly classifies small fibrations. Classifies small fibrations. And what I mean by this is that such pullbacks exist. Meaning for all p, there exists a pullback as above. So there exists a classifying map as a pullback. So that would be like surjectivity of that pseudo-natural transformation. It's saying, well, it's literally that. It's exactly surjectivity on objects, I suppose, of the pseudo-natural transformation. But actually what we're going to require is a bit more and a bit mysterious. Let me give the definition. So what I'm going to mean, is that too high for Zoom? Maybe. Okay, close enough. So here's the definition. So now I'm going to turn universal fibration into a technical term to reflect exactly the condition that we want. So a map, pi from u tilde into u. Sorry, let me explain what E needs to be for this to work. So let E be a model category with all objects cofibrant. With all objects cofibrant. And if these words don't mean anything to you, you can say let E be the category of simplicial sets. I'm highlighting some special properties of simplicial sets that make this argument work. And if simplicial sets don't mean anything to you, remember that's OK to black box as well. So cofibrant means, means nothing. I'm working classically in simplicial sets also. OK, so in model category with all objects cofibrant. So then a fibration, small fibration. So that's a pi u tilde over u. So that's a fibration in this model category. That's part of the model category structure for simplicial sets. This means confibration is a universal small fibration. I may say on occasion just universal fibration and forget that I'm trying to be a little careful about sizes. If for all cofibrations, which in all the categories, all the model categories that we're interested in just mean monomorphisms. So perhaps that's clear. At some point, I'm going to require the cofibrations are the monomorphisms. So just maybe I should stick with monomorphisms. So that'll be called an I from A to B, and it'll be indicated in symbols using this tail. Then whenever I have a lifting problem, so I have this comparison map induced by pi between the representable functor. This is in my category of pseudo-functors from E to groupoids. And here is what the fibrations form. So this is the groupoid valued pseudo-functor of all the small fibrations. Well, I could also form the representables associated to this A and B, and by Anita, composition with I induces a map here. And what I want to say is if I'm given any lifting problem like this, there exists a solution. Okay, so this is the definition of being a universal fibration. What the heck does it mean? So the first thing I can do is I can unpack this into sort of a more concrete property of U. So unpacking, what does this lifting property say? So firstly, the data of the lifting problem is as follows. So I have a map between representables. That's just given by a post-composition with some map H. So I have an H, which is a morphism from A into U. I have this I, which is my monomorphism, which goes from A into B. Now, U, of course, is the codomain of my universal confibration, which is here. And when I compose this way around, this composite by the Anita lemma corresponds to a specified small fibration over A, which I'll draw in here. And that small fibration is obtained as the pullback along this map H. Similarly, along the bottom, the data of this map specifies a small fibration with codomain P, just by the Anita lemma. And then the commutativity of the square says that when I take P and I pull it back along I recover my D. So the lifting problem presents to me a pair of pullback squares involving fibrations arranged in this configuration. Now, a solution to that lifting problem, so that's this dashed diagonal map. So by Anita, that corresponds to a morphism K from B to U. So I can stick my K into this diagram. And the fact that the top triangle commutes just says that K restricted along I is H. So in other words, I get commutativity of the bottom triangle in this diagram. And the fact that the other triangle commutes says that when I pull back my universal fibration pi along this K, I recover P. So in other words, there exists a pullback square here that is compatible with that pullback square. So this is the essential property that defines a universal fibration, which I'm making into a technical term using this definition. So I think it'd be great if this property had a name. So some names that appear in the literature are sort of acyclicity. It's also called strong gluing. It's also called the stratification property, or maybe the fibration stratification property. So this is the term of Mike Schulman. This is a term of Carla Angiuli and John Sterling. This is a term of Raphael Stenzel. I'd love for there to be a consensus term for this property because I think it's important and it deserves being highlighted further. So what is this good for? So one immediate corollary of the definition, sort of an easy lemma, is that if I have a universal fibration, so if my pi is a universal fibration in the sense of this extension property, maybe I'll give it a star. So this property is what makes a universal fibration. Then pi weakly classifies fibrations. I suppose in the form of the definition I wrote here, I should say it's the universal small fibration and weakly classifies small fibrations, but that's what we're trying to avoid. So what's the proof? Well, I just sort of take A to be empty in this diagram. So my hypothesis that all objects are cofibrant means the unique map from the initial object into B is a cofibration. And so I can apply this lifting property where that back of the diagram disappears. And what it says is now for every fibration P, there exists a square like this that classifies it. So it's exactly the weak classifying property. So I guess that's some good news. So there will be other applications of this specific acyclicity property later on, and I'll return to it for now. But maybe we just have to take it on faith that this is a good idea. Because the next thing I need to address is how on earth do we find one? So we motivated this discussion as how on earth am I going to find a universal fibration? Now we at least know what a universal fibration means, so I suppose that's some progress, but I still haven't given you any indication how such a thing could be constructed. So the question that remains is, how do we find one? Okay, so there are various techniques for building the universal fibration. The one that I'm going to, yes?
Is it clear from the axioms that you get a bijection from pi naught of k to the EU?
That's a good question. Well, so from pi naught, it is now, yes. I mean, you get as a bijection, I see. So what I have is surjectivity on objects, and you're asking, I'd have to think about that. So let's leave that as an exercise. But yeah, interesting question. So, okay. Yeah, I mean, we're going to have a stronger, relationship once we introduce univalence, which will tell us, I mean, it'll in particular relate homotopies between maps in the base and equivalences between the fibers. But Maybe there's something more elementary to say, but I'm not going to be able to do it fast enough to answer that right now. Okay, so we would like to construct an example of one of these universal fibrations. There are various techniques for doing so. And the one that I want to highlight, because it works in somewhat greater generality, and also I just think is cool, is something called Hoffman-Streicher universes. So the technique that I'm going to develop, so what this will do is this will construct a universal small map. So Hoffman-Streicher universes aren't directly about fibrations, but just about maps with no further restriction. Though we'll see that we can adapt this technique to get a universal small fibration in any pre-sheaf category. In any pre-sheaf category, but rather than introduce notation for a general pre-sheaf category, I'm going to continue to let E stand for the category pre-sheafs on the simplex category, in other words, this category of simplicial sets. So, right, and here I am going to be a little bit careful about sizes, so I'm going to write sort of set to the kappa inside set, and simplicial set to the kappa inside simplicial sets for sort of a regular cardinal kappa. And what I mean by this is I'm reducing to sets of size kappa, and I also don't want there to be too many sets in any given isomorphism class. And then this is just functors valued in here. I'm putting the decorations where they're going to be out of the way. So that's why one's a superscript and the other one's a subscript. Okay, so how do Hoffman-Streicher universes work? So again, let's review the Yaneda idea. So the Yaneda idea, again, our intention is to define a simplicial set, or really a map of simplicial sets. So this will be a large simplicial set, so it won't live in that subcategory with a kappa, but in the large one. So I want to define something like this. And the Yaneda idea was to take Vn to be the collection of small maps. So E over delta n, I'm going to call that small maps. So I've changed my notation from U to V because I'm talking about arbitrary maps, not necessarily fibrations. I'll bring U back when we restrict to the fibrations. So this was the Yaneda idea. And again, the problem with the Yaneda idea was as follows. So these small maps live in this category of simplicial sets, I guess small simplicial sets, kappa over delta n. So my E lives in here. And when I pull it back along some simplicial operator to delta m, this is pull back along alpha, this was a pseudo-functorial action. So if I pretend I've solved the size issues, when I pull back, I'm defining not a simplicial set, but a simplicial groupoid or something like that. I still have this coherence issue. But here's the solution. So there's an equivalence of categories between the category of small simplicial sets over delta n and the category of pre-sheafs valued in small sets on the slice category. So this over n op. The op should be on the outside here, but I don't want to write so many parentheses that nobody can read anything. So this is a sort of well-known equivalence of categories that works more generally for any, it doesn't require that the base here is representable for any pre-sheaf and any pre-sheaf category. The slice category over that pre-sheaf is equivalent to the category of pre-sheafs on the category of elements of the slice. But in this case, the category of elements of this delta n is this category, which is the slice category of delta over the object n. Okay, so of course I have a similar equivalence of categories here. Again, this op should be read on the outside, so this is pre-sheafs on the slice category. And the reason for passing through this equivalence is on this side, the action of a simplicial operator is given by a precomposition. So this is a precomposition with what I'm going to write as alpha shriek. And what alpha shriek is it's the functor from the slice category over n. So alpha, again, is a map in delta from m to n. So if I have something in the slice over m, I can just compose with alpha and get something in the slice over n. And the key thing to note is on this side, this is a pseudo-functorial action. Pseudo-functorial action. Pullbacks compose up to isomorphism, but here this is strictly functorial. Strictly functorial. So the definition of the Hoffman-Schreiker universe is rather than define Vn to be the set of, so this Yaneda idea was defining this to be the set of objects in this category on the left, in the category of simplicial sets that are small over delta n. So this is not what we're going to do, because this would define a pseudo-functor, a groupoid valued pseudo-functor, as opposed to a simplicial set. However, if we pass across this equivalent category, that will be the right thing. So instead, I'm going to define Vn to be the objects in this category of small presheaves on delta n. So again, I'm defining this for every n, and so this is giving me a family of sets, and I use these strictly functorial actions to turn this into a simplicial set. So this solves the coherence problem in the sense that V at least is a simplicial set. Okay, so I want to define also this V tilde in the map. I should say what this V does. So how do we think about an element in Vn, or an element in V? So again, what I'm saying is that A in Vn is, by definition, is a functor from A. So it's a functor called A. That's a presheaf on this category, valued in small sets. So in particular, it takes any object in this category, so that would be some alpha that goes from m to n, and gives me a set, which I might just write as alpha A. And a key fact is from this, I can pass back across that equivalence of categories that I mentioned above and construct a simplicial set that lives over delta n. So from this A, which is a functor, I can construct a simplicial set. How is this defined? So if so a simplicial set, again, is a family of maps of sets. I can think about the M simplices. So now this is a map of small sets. Previously, this was a map of small simplicial sets. And my alpha can be thought of as an element in the base over here. So this is just a map of sets. I can tell you what this map of sets is by telling you what the fibers are over every element in the base. And it's exactly the set alpha A. So that's the subset of this fiber, the subset of this set that maps onto this alpha. That's how this correspondence works. Okay, so I would also like to define this V tilde n, and there's a definition that's really quite simple. So rather than take small set valued presheaves on the slice category delta over n, I can take things valued in pointed sets. So I'm adding a little asterisk here. And what I mean by this asterisk is I'm going to say sort of pointed set valued presheaves. Pointed set valued presheaves. So one thing to notice about the indexing category here, delta slice over n, is that it has a terminal object, namely the identity map at n. So when I take an op, that means this category has an initial object. And so if I'm looking for a functor from a category with an initial object into pointed sets, I only have to choose the point in the set that's the image of the initial object. Then the fact that these are pointed set preserving maps means that that point is the only point I pick. So really the data of a thing here is given by, so a pair AA. So an element in this, an n simplex in this simplicial set is a pair AA, where A is exactly as before. And I can think about the data of this point in two different ways, depending on whether I'm in this perspective or in this perspective. So here I could think about this A as a global section. So in other words, A is an element of A at the identity map at n. That's what I was saying, is I just take the image of the initial object and pick a point in that set. Or equivalently, so if I represent A as my small map over delta n, then what this A is a section. So by the Anita lemma, map from the n simplex into here is going to identify an element in the fiber over the identity at n, and that's exactly what that is. Okay, so this is the definition of the Hoffman-Streicher universe. So that's nice. That's a very explicit construction. But what's also nice is it is a universal small map in the sense of this definition. So let me record that, and then we'll start to get some mileage out of this observations. So I think this observation was first made by Szynski. So a lot of people attribute, so this lemma in this form is originally due to Szynski, but there's also a nice exposition of it in a paper of Orton Pitts. More precise citations for everything are in the lecture notes. This pays attention to the constructive reason, the classical reasoning that's required in the proof here. In any case, the statement is that the Hoffman-Streicher universe, so that's this pi from v tilde to v. So pi is just the evident forgetful map, forgetting the point in a pointed set, is a universal small map. I'm not going to say small fibration because it's not a fibration. We haven't talked about fibrations, but it's a universal small map. And what I mean by that is I can think about the functor represented by the base. Pi defines a map not into fk, because those were the fibrations, but into this E kappa, which were the small maps, because it is a small map. And I'm going to demand exactly the same lifting property indicated here, sort of for all monomorphisms in my category E. Monos. I think for Szynski, monomorphisms and cofibrations are the same thing, so I'll phrase it like this. Okay, so the proof requires some classical reasoning and frankly makes my head hurt, so I'm not going to discuss it any further, but anyway. Yeah, so this is a key property of the Hoffman-Streicher universe. Okay, so now I'm going to move finally into the simplicial model. So into the simplicial model of univalent foundations. And our first goal is to construct a universal confibration. So I would like, I finally want this universal confibration that I've been promising all along. And how do we do it? I'm essentially just going to adapt the Hoffman-Streicher universe technique. So now I'll just give the definition. I'm going to define U of n. So our Yaneda idea that didn't work was to just take confibrations over the n simplex. What I can take instead are, I don't know, maybe one way to say this, I'm just going to take the elements A that belong to the Hoffman-Streicher universe, Vn, which remember are not literally confibrations. What they literally are, again, are these sorts of presheaves. However, from such a thing, I can unravel it to get a small map. And when I do, so when I take the corresponding small map by passing across that equivalence of categories, I want this to be a confibration. So in particular, so I'm making a set theoretical definition because I'm working in a category of sets. We're working in simplicial sets now. So I'm defining this U in such a way as to be a subset, a simplicial subset of V. So this definition gives me a simplicial set U together with an inclusion into V. And I'm going to obtain the universal fibration, sort of the map part of this, just by pulling back. So more explicitly, maybe I'll keep that just as a reminder. So more explicitly now I'm going to define this U tilde and pi to be the pullback along the Hoffman-Streicher universe along this sort of natural inclusion. This, remember, we're defining just as a subset of some other simplicial set. Okay, so great. So we'd like to start proving some stuff about this. I mean, I'd like to be able to prove that this is a universal confibration in the sense of that definition. So there's a key ingredient about the fibrations of simplicial sets. So this is a key axiom that they satisfy, and it'll play a big role when we come back and discuss generalizations, which is as follows. So the confibrations, of simplicial sets are local. So simplicial sets are local. And what I mean by local, sorry, let me just emphasize this diagram above what's in simplicial sets. So we have the Hoffman, we have the thing that I'm claiming is going to be the universal confibration, but we don't know anything about it yet. So a key thing we're going to use is that confibrations of simplicial sets are local. What that means is that a map from E to B is a confibration if and only if all of its pullbacks over simplices are confibrations. If all of its pullbacks along any map whose domain is a simplex and representable are confibrations. Okay, so in this proof, I'm going to finally give a definition of a confibration. So what is a confibration? So it's a map of simplicial sets that has a right lifting property with respect to a certain set of maps of simplicial sets, which are called the simplicial horn inclusions. So this is the n simplex. This is some simplicial subset that removes the face opposite vertex k and also the interior. This map is certainly a monomorphism, and it's also one of these weak homotopy equivalences. You can imagine a deformation retract of a simplex onto the horn. And what characterizes the confibrations are this lifting property. Now, an argument that we've used on a few occasions is that when I have a lifting problem of this form, I might as well just pull back the map on the right along the codomain. So I can pull back this E to maybe E over B, which lives here. And you can see that a solution to this lifting problem is equivalent to a solution to this right-hand lifting problem. And now we can see the locality right here. So if P is a confibration, confibrations are stable under pullbacks, so certainly these pullbacks are confibrations. Conversely, if the pullbacks are confibrations, then when I'm presented with a particular lifting problem involving a particular B, I pull back to that fiber and I solve it there. So that's the locality of the confibrations. Okay. So the first thing we can get out of this locality is, all right, I can't do that at the same time. Just wait a second. Right, so the first thing that we're going to get out of this locality is the fact that this thing that I'm claiming is the universal small fibration. This map pi between u tilde and u is in fact a fibration. So that's the first corollary. So I can claim that, or I can prove now that u tilde is a confibration. Why? Well, by definition, its pullbacks are confibrations. It's the fibers over any simplex. So proof, sort of, by definition, these pullbacks are confibrations. Confibrations. Great. So being a confibration is a good start. I suppose I should observe also that it's a small confibration. The base here is a large simplicial set, but the fibers are small simplicial sets because they were defined exactly this way using Vn, and Vn are pre-sheaves valued in small sets. So this is a small fibration. I still need to argue that it's the universal small fibration satisfying that definition above. And for that, we're going to take advantage of another point of view on this locality property, which I'm going to frame as follows. So this is another lemma about locality. And what does it say? It says that a map of simplicial sets is a confibration. So is a confibration sort of if and only if its classifying square to the Hoffman-Streicher universe factors through the pullback, which I have here. So if and only if its classifying square really any classifying square to the Hoffman-Streicher universe. So we've proved, this should be a small map. We've proven that Hoffman-Streicher universes, since they're the universal small map, are indeed small map classifiers. So by that lemma up there, they're a weak classifier for small maps. So for any small map, there exists a pullback like this. The statement is this small map is a confibration, sort of if and only if this classifying square factors through the classifying square that defined the universal confibration from the Hoffman-Streicher universe. So factors through this. Okay, so what's the proof? So one direction is very clear. If I have a factorization through this, since I've proven this is a confibration, its pullback will be a confibration. So what's interesting is the other direction. So suppose in this case that this thing is a small confibration, Okay, so what am I trying to do? I'm trying to argue, I need a little bit more space. So I'm trying to argue that this particular classifying map here, I'll call it decorated in that way. So I want to show that a particular map of simplicial sets, this P that goes to V, lands in a simplicial subset U. Once I have the factorization of the codomain, then this will factor by the universal property of pullbacks through that pullback rectangle. So this is a simplicial subset. What does a simplicial subset mean? It means for all n simplices here in the image of this map, those would lie in the subset. So what I really need to show is that for all n simplices of B, the composite here factors through the subset. So to prove that I have a factorization there, it suffices to prove that I have the factorization when I restrict to the n simplices. This is some sort of generating property of n simplices in a simplicial set, the representables in a presheaf category. But this is going to be true by definition. So what locality says is that if I have my P over B, that's a confibration. Well, that's going to tell us that the pullbacks over here are confibrations. And this was defined to be exactly the subset here of those elements that when I pull back, I don't just get a small map, I get a confibration. So this is another reflection of this locality property. Okay, so put more abstractly, so therefore, a conclusion of this lemma is as follows. So I have on the one hand the Hoffman-Streicher universe V. E here is the category of simplicial sets. I have on the other hand this universe for confibrations U. And in each case I have the natural transformations that land here in the groupoid valued pseudofunctor of all small fibrations. And this is the groupoid valued pseudofunctor of small maps. So this again is a diagram that takes place in the category of groupoid valued pseudofunctors on E. So I have this diagram. This is using the inclusion. These are using the classifying maps. This is just observing that this thing is indeed a small fibration, as we've mentioned above. And what I've just argued by locality is that this is a pullback. So maybe at least when probed by representables, but that's going to be enough that if I have a map into V that is in fact a small fibration, then it factors through the pullback here. And as a corollary of that, I can prove that, finally I can prove that this U tilde to U is a universal small fibration. So the definition of this universal small fibration is this still mysterious lifting property that was described above. What I need to argue is that for all monomorphisms in the category of simplicial sets, if I'm given any lifting problem in this category, so that's of this form over the fibrations, there exists a solution to that lifting problem. But what I've argued is that I have this pullback square and what I've proven is the corresponding locality property for the Hoffman-Streicher universe. So there exists a solution to this lifting problem, and by the universal property of pullbacks, that induces the solution that we require. Okay. So now we finally have a universal confibration. Any questions? Yes?
This construction here, when you go from a pseudo-functor to something that's strictly functorial, can you give some intuition for where the weak data goes? What happens to it?
I mean, an equivalence of categories so does not induce an isomorphism on sets of objects. Maybe that's a thing to say. So, you know, if, where did I write here? So if that object set were isomorphic to this object set, I'd be able to translate across the strictly functorial action to a strictly functorial action. But it's in there. It's in that equivalence. Yes?
The first word you wrote was classical. Where did you, what whole thing was classical?
Right, so I meant classical in the sense of classical reasoning. So law of excluded middle is features very heavily in that proof. And in fact, the Orton-Pitts paper kind of discusses the fact that the analogous result would fail constructively. So that I meant classical in the sense of classical reasoning. And so it's law of excluded middle. What you do is you reduce to the case where B is a representable, and then A is a sieve on a representable, so a simplicial subset of a delta n. And then you sort of define the data of the extension by cases, depending on whether your map to delta n is in the image or not. But it's a delicate argument that makes my head hurt, frankly. Yes?
To what extent can you play the same game with a general pre-sheaf category?
Literally everything that I've said so far here applies for any pre-sheaf category, provided that my notions of fibration in the pre-sheaf category are local in this sense. And perhaps I'm using that the cofibrations are monomorphisms. So yes, and there's a reason. So this is not the way that the universe is built in the Voivodsky paper. I'm presenting it in this way because it suggests some generalizations. Though we'll see it's not going to generalize far enough. This won't actually be that useful on Thursday, though this perspective on universal fibrations will be, and that's kind of why I'm sort of forcing us into that more abstract perspective. Yes?
I was wondering what would be the advantages of pre-construction, direct and pre-construction, such as the one you have exposed, compared with the use of more general coherence theorems such as Anabel.
Such as what?
Anabel.
Oh, right. So you still, so there's, I believe the coherence theorem that you were alluding to, though we'd have to talk after, refers to the coherence problem associated in taking a universal fibration and then, taking a kind of weak model of type theory, meaning you have kind of weak stability of all the type forming operations, and turning it into a strict model. So this coherence problem was different, or I think about it as being different. It's about defining a simplicial set at all.
Okay.
Yes?
So the simplicial model of hot is known to be non-constructive. Is it mostly because of this classical thing in the corner, or is it other stuff as well?
So another non-constructive aspect, so I believe it is necessary in this definition of the universe, or maybe at least the proof of some of the properties of the universe. Another non-constructive aspect involves univalence, the proof of univalence, which I'm hoping to get to, so maybe I'll press on. Yeah, so I mean, it's specifically the verification of the univalence axiom that's not constructive and in the simplicial model, but perhaps among other things. I mean, building the model structure, there's some non-constructive aspects. There is a constructive version of the Quillen model structure, though it's a bit different than I'm using here. There are experts on these topics that those questions should be directed towards. Okay, so we have finally, I've been claiming along that we're going to get some sort of universal confibration. We finally have it. So we've constructed an explicit map between simplicial sets and given a precise notion of what it even means to be a universal fibration and proven that this does satisfy those properties. So there are some additional desiderata of the universal confibration, and that's what I'm going to turn to next. So the first one concerns fibrancy of the universe. And what I mean by this is in the simplicial model, we would like, so this universal fibration is going to play kind of two dual roles. On the one hand, it's this thing that's going to kind of induce the coherent type theoretic structure on the entire model. But when, in fact, I build two of these universal confibrations, so this one involves some regular cardinal kappa. Soon I'll want it to be an inaccessible cardinal. If I built another one involving, say, a smaller inaccessible cardinal lambda, that latter one would then define a universe inside the larger one. So it will be the model of, it'll be an object in the contextual category that's built from the universe. And so that should be a type in particular. And for that reason, I would like it to be a fibrant object, because the types in the simplicial models are fibrant objects. So that's the next thing that I would like to prove is, so we would like the simplicial set U, which is a simplicial set, to be a concomplex. What on earth does that mean? So the definition of a concomplex, which I'll finally give, is that it means that for an arbitrary map here and an arbitrary acyclic cofibration here, being a concomplex means there exists an extension of this map along that acyclic cofibration. If you're expecting a different definition that involves these Horn inclusions, which might still be somewhere, that is equivalent to the one that I'm giving right now. So let's think about this condition. So if the universe strictly represented small fibrations, so strictly represented this thing here, this definition would unpack as follows. So remember, this is not the case. I do not have an isomorphism between the representable functor at U and this functor of fibrations, small fibrations. But if it did, I could translate this condition as follows. So this is something that's called the fibration extension property. And what's interesting about it is it's really just a property of the ambient category, not specifically referencing the universe. So a model category E satisfies what's called the fibration extension property. The fibration extension property sort of if and only if. So the setup to this lifting problem is a map from A into the universe. So we could encode that as a small fibration over A. The other part of this lifting problem is my acyclic cofibration here. The desiderata is to extend this map to a map here, which would then classify as small fibration over B. So if I had a bijection between maps into the universe and small fibrations, what that would amount to is that given a small fibration over A and an acyclic cofibration, there exists a small fibration over B that pulls back to the original one. The pulling back condition is giving us the commutativity of this diagram. So the fibration extension property so the fibration extension property is kind of a moral restatement of the fibrancy of the universe. And again, what I mean by moral here, so moral in mathematics means like not literally true. So if I had a bijection between maps into the universe and small fibrations, it would be that. But it's not quite that, because that's not what the universe is. Being a universal fibration does not provide us that bijection. Nevertheless, these properties are very closely related using the defining property of a universal fibration, and I'll prove that for you now. So let me keep this definition up here, and I guess I'll keep that as well because we're about to use it. So the lemma is that if I have a universal fibration, so is a universal fibration, and again what I mean is exactly this acyclicity property that I've unpacked there, then the base U is fibrant if and only if the fibration extension property holds. The fibration extension property holds for the category E. And again, this is what's really interesting about this statement. On the one hand, I have a statement that a particular object in my category is fibrant, which is, I don't know, it seems like a special property of a particular object. Here I have something which does not mention the universe at all. That fibration extension property doesn't mention U or pi or U tilde. It's just a property of the model category. And I mean, the connection is in this notion of universal fibration, which relates a particular map to the fibrations in a model category. Okay, so this argument again is general to model categories, maybe at least with cofibrations being the monomorphisms. Let's give a proof. So suppose, firstly, that U is fibrant. And let's argue and consider, so I'd like to consider this fibration extension problem. So I'm considering in this case a small fibration over A and an arbitrary trivial cofibration here. So since the universe is a weak classifier, so since pi weakly classifies small fibrations, classifies small fibrations, the fact that I have a small fibration P, I think I called it Q above, let me change my notation. The fact that I have a small fibration Q at all means that I can construct a classifying square into the universal fibration. So there exists somehow this classifying square here. Right, so now I'm in this setting. So in particular, given this classifying square, I get the data of a map from A into U. My hypothesis that U is a fibrant object means there exists an extension here, K. So here's my map J into B, and I have this K. And now I can just form the pullback of pi along this map K to obtain a fibration here P. And then that pullback factors through the back pullback to give me the pullback square that I desire. So this is a verification of the equivalence extension property, the fibration extension property. Here's the fibration that I've extended given univalence. Let me use the rest of this board to complete the proof. So conversely, if E has the fibration extension property, I would like to show that U is fibrant, so I'm going to consider a lifting problem. So that's something like this involving an acyclic cofibration J. I would like to construct a solution to that lifting problem. So using this classifying map H, I can pull back the universal fibration to get me some fibration here by a pullback. Now using the fibration extension property, I can extend that fibration to a fibration here that pulls back to the original one. And I'd be kind of stuck at this point were it not for the fact that I have this acyclicity property that I suppose is right here, which is that in this sort of configuration, I'm entitled to an extension here and an extension here that factors the back pullback through the front pullback. And in particular, this K is my solution to the lifting problem. So you can see that this sort of mysterious property that defines what it means to be a universal fibration features in a central way in tightening up this moral equivalence between the fibration extension property and fibrancy of the universe. Okay, so I have 15 minutes. I want to say something about univalence. I guess we'll just start here. Okay, so the other desiderata of this universal fibration is that it should verify Voevodsky's univalence axiom in the model category. And I'm going to say more about the statement of that univalence axiom than the verification of it, but I'll say something about both things. Firstly, I want to give the hypotheses on the category E. So these are all facts that are true of the category of simplicial sets, but I'm highlighting here because these are really the essential ingredients in the proof, and everything I'm going to say would hold in that greater generality. So the first thing I'm going to require is that E is simplicially locally Cartesian closed. Locally Cartesian closed. So E is firstly a Cartesian closed category in that its composition between the slices has a pullback right adjoint and then a further push forward right adjoint. But moreover, E is a simplically enriched category, tensored, cotensored, and those adjunctions are all simplically enriched. The next thing I want to say is that E is a simplicial model category. So what this means is that E has these notions of fibrations and cofibrations and trivial fibrations and acyclic cofibrations. And moreover, that structure behaves well with the simplicial enrichment. Then finally, I'm going to require that the cofibrations are monomorphisms, which is a hypothesis I've made. And the model structure is something called right proper. I'll mention that property when I use it. Structure is right proper. So I get that all of these terms are not necessarily familiar, but they are Googleable. So that's the intention of laying it out like this. So where do I use these sort of hypotheses? So it's in a construction that I mentioned at the very start last time that I'll revisit now. So if I have a fibration E between fibrant objects, then there exists this relative path space, fibered path space factorization. Fibered path space factorization. So the thing that I'm factoring is this fiber diagonal, which I'll draw now. And the content of this statement is the model categorical properties of this construction, which I'm going to exhibit along the way. So how this construction works is I start by factoring the, sorry, I'm going to need a lot more space. I start by factoring the ordinary diagonal for E. So that's the map from E to E cross E, which is given by the identity on both components. Through here, I'm using the simplicial cotensor with delta 1, so that's part of this simplicial enrichment. And a property, because E is a simplicial model category, this map is an acyclic cofibration, and that map's a fibration. So that's where those hypotheses come in. So I can perform the same construction along the bottom for B. So since P started life as a fibration between fibrant objects, I get these fibrations going down. And now what I'm going to do is I'm going to pull back the top fibration or top factorization to live over B. So last time I used horrible notation for this, but now I'm going to use better notation. So this is going to be called PB over E. This is this fibered path space of the statement. And so by right properness, this weak equivalence here pulls back to a weak equivalence here, which by 2 of 3 makes that a weak equivalence. Because cofibrations are monomorphisms, and this factor is a monomorphism, that's a monomorphism, so this map is a trivial cofibration. And then similarly, I can pull back this E times E all the way over here, and that gives a construction of just the pullback of the map P along itself. And this map, induced by the universal property of pullbacks, is a fibration. I think last time I maybe mistakenly said it was a pullback of this fibration. It's not, in fact. It's a pullback of the fibration that lives in this square from this map to the pullback. But again, by the simplicial model category axiom, that map is a pullback. So this is a fibration as a pullback of a fibration. So this part of the construction here so maybe I'll just highlight in yellow, is this relative path space factorization. And that's an illustration of how these hypotheses are going to be used. Okay. Right, so I should remind you what the homotopy type theoretical statement of univalence is. And then I'm going to, as quickly as I can, give the model categorical analog of that statement. Yes? Great. I'm not familiar with that. So the question was whether the stratification property, which is the meaning of being a universal small fibration, connected to the stratification property in Grothendieck's writing on something that I have no familiarity with, so I don't know. But, no.
No more question? Yes.
Yeah, thanks. So you constructed a universe in simplicial sets. I imagine that it's closed under like dependent functions and.
Yes.
My question is how do those relate to the dependent functions that will be present in the model, like just as a pre-sheaf category?
Great. So, right. So I think for the construction of the universe that I gave, I demanded only that we were dealing with a notion of smallness with respect to a regular cardinal. So if I'm interested in that universe being closed under various type forming operations, I should require it to be an inaccessible cardinal. And to be a little bit more precise about what the notion of closure involves, we have the definition, we have the following notion of an internal universe. So this is in respect to the notion of universe that I started with today, which is just a map in a category with specified pullbacks. So given a universe, so you can think about this as being the universal fibration, but really much less would suffice in some category E. And internal universe, so this is meant to be sort of structure that I'm adding to this U that would mean that in the contextual category built from this U, there's a universe in there. So an internal universe is given by, so there's two bits of structure. Firstly, I want to map from the terminal object of E into U. So it follows then that I can use my chosen pullbacks along this universe to define an object that I might call U sub 0. And then I need, and also a map from U sub 0 into U, which you can think about as being the map that would take so if this internal universe is like the even smaller types, this is the map that would embed a small thing into a large thing. So the theorem about this notion is that if U has an internal universe, then EU, the contextual category that we built from U using Voivodsky's construction that I discussed previously, has a universe. And what is it? So it's this U naught. So remember, the objects in this contextual category were sequences of morphisms starting from a map from the terminal object into the universe. So this U naught gives a type in here in the empty context, and that is going to be the universe inside. So the model of homotopy of dependent type theory lives in here, and this is giving us a universe inside there. So your question was about closure under type forming operations. So I can say that an internal universe U naught is closed under, let me say, identity structure, which is the type forming operation that I meant to discuss last time and is at least in the lecture notes. You can read what that means there. If firstly, sorry, one other thing to mention is once I have this map, I from U naught into U, I can pull back the fibration, or I can pull back this map pi. I have a chosen pullback, and I get a map pi naught and this object U naught. So this being a universe in the sense where it just means that it's a map with chosen pullbacks, induces a universe structure on the internal universe. So what it means to be closed under identity structure means firstly that pi naught has the identity structure as does pi, structure as does pi, and this is preserved by this square. So in the case of identity structure, what that involves is a particular factorization, a chosen factorization of a relative diagonal map and an internal lifting operation. So all of these are defined using limit constructions and morphisms on these objects, and so this square will induce a map between those, and it's just meant to be commutative. So there are similar definitions for all of the logical structures. And then in the simplicial model, I'm going to let lambda less than kappa be inaccessible cardinals. Then we can just think about the universe that we've constructed using the Hoffman-Streicher technique, but for two different inaccessible cardinals. And this will be a universe, and this will be an internal universe, and they'll be closed under the type-forming operations such as pi's and identity structure and everything. So that's how that goes. There's a little bit about that in the lecture notes, and a lot more certainly in the Kapulkin-Lumstein paper about the simplicial model.